In today's video, we're going to look at a few more reactions of carbonyls. The first one I want to talk about is how alpha-beta unsaturated carbonyls work. And so we'll start with some general nomenclature or syntax. This carbon is the carbonyl carbon. The carbons next to that are alpha carbons. And the next one down the chain is a beta carbon. And we can keep going down the chain, but we just need alpha and beta for the purposes of this discussion. And an alpha-beta unsaturated carbonyl just means that there is a double bond between the alpha and beta carbon to a carbonyl. These structures have some extra resonance. And so if we look at the resonance of a carbonyl, we get this resonance structure. But an alpha-beta unsaturated carbonyl has one extra resonance structure that looks like this. And what that does is give us a partial positive on both the carbonyl carbon and the beta carbon. So we can fill those in on the original structure. This guy has a partial positive charge. The oxygen still has a partial negative charge. But now the beta carbon also has a partial positive charge. And that leads to both the carbonyl carbon being electrophilic as well as the beta carbon is electrophilic. Since carbonyl carbons have two sites that are electrophilic, there are two places that you can add, or two types of addition that you can do. And so the first one of those is conjugate addition, and this is going to be 1,4 addition. And that results in the addition at the beta carbon. And so the product of a conjugate addition is the addition at the beta carbon where the ketone stays intact. In order to form this type of product, you must be under thermodynamic conditions and those include long reaction times and high temperatures. Now, these things can be relative to one another, and so you have to look at this in the context of other alpha-beta unsaturated ketones and those additions. But in general, the longer reactant times and higher temperatures favor thermodynamic conditions. You also have to have a weak base for a nucleophile, so your nucleophile must be a weak base. Some examples that you might see of this are alcohols, thiols, and we've just seen cyanide, which is a weak base. If we look at the mechanism, I thought we would look at another example using methanol as our nucleophile. And in this case, I have an acid catalyst, and that should be a red flag that the first thing you're going to do is protonate something. And so we're going to protonate the ketone to form this intermediate, which is more electrophilic than the normal ketone. And so that activates this towards nucleophilic attack. And I'm going to attack the beta carbon. That's going to kick these electrons over and kick those electrons up. to form this intermediate. Then some base is going to come in and deprotonate to give this. And this structure we have seen before in the hydration of alkynes, but this structure here is called an enol. And enols tautomerize under acidic conditions. And so I just formed this acid, and I'm going to protonate my alkene and kick some electrons down at the same time, and that is going to produce this intermediate here, where I've just added a proton there. And in a final step, some base is going to come in. The oxygen should have had a positive charge and pick up this proton to give the final product. With the ketone intact here. Alpha beta unsaturated carbonyls are also electrophilic at the carbonyl carbon. And so direct addition or 1,2 addition is an addition at the carbonyl carbon. And sodium borohydride would be an example of a nucleophile that would react at the carbonyl carbon. And so if we draw out this mechanism, we've got a BH4 minus, and that hydride just comes in and attacks here to give this intermediate, which I have written water here, but really this probably ought to be H plus and water. And then in a second step, we add H plus or H3O plus and pick up that water or that proton to generate this product. These conditions, if addition at the beta carbon occurred under thermodynamic conditions, addition at the carbonyl carbon occurs under kinetic conditions. And these tend to be short reaction times and low temperatures. Often, the nucleophiles involved in here are strong bases. So this includes things like hydrides we just saw, Grignards, and organolithiums. I want to take a brief detour here to review organometallic reagents and their relative strengths. And so for starters, we can form several organometallic reagents if we start with an alkyl bromide. And so in this case, I've got cyclohexyl bromide or bromocyclohexane. And if I treat this with lithium metal, I can replace that bromide with a lithium to create an organolithium. If I treat that same alkyl bromide with magnesium, I'm not sure why I'm numbering these. I'm going to get rid of that. Magnesium, I can make a Grignard reagent, but instead of completely displacing the bromide, magnesium inserts itself in between the bromide and the magnesium, or in the carbon. And the last one we have talked about this semester is forming alkyl cuprates or organocuprates. And those get formed from the organolithium. So the first thing I have to do is form the organolithium. And then in a second step, I'm going to add copper iodide. And this is going to be a half equivalent compared to the organolithium, because alkyl cuprates attach to alkyl groups to copper. And you get a complex with lithium as well, like so. I wanted to review this because organolithiums are very strong. In fact, they're the strongest nucleophile that we talk about in terms of organometallics. And alkyl cuprates, by comparison, are the weakest. And so they have slightly different reactivities with alpha-beta unsaturated carbonyl groups. If we look at several examples of organometallics with alpha-beta unsaturated carbonyl compounds, the organolithium is the strongest, the hardest nucleophile. And so it's going to preferentially attack at the carbonyl carbon. And so this reaction is going to form this alcohol where I have added an ethyl group to the carbonyl carbon and then protonated it in a second step to form this alcohol. Alkyl cuprates, on the other hand, are weaker nucleophiles, and they will actually favor addition at the beta carbon. And so this particular structure, I expect to form this intermediate where I have added at the beta carbon my ethyl group and kept my ketone intact. Grignard reagents are in the middle, and so if the alpha carbon is sterically unhindered, such as in an aldehyde or maybe a methyl ketone, addition at the carbonyl carbon is going to be preferential. And so for this aldehyde, I expect to add at the carbonyl carbon. However, if you increase the steric bulk of your alpha carbon by, say, putting a isopropyl group there, the kinetic addition becomes addition at the beta position. And so sometimes you can see conjugate addition or 1,4 addition with Grignards, especially if the alpha carbon is sterically hindered. We're going to switch gears a little bit and go back to normal ketones and talk about the Wittig reaction. The Wittig reaction is a very excellent way to make alkenes. And a Wittig reaction is going to take a carbonyl and a phosphorus ylide. That's what this thing is called, an ylide. And it's going to form an alkene out of this that looks like this. And so this part of the molecule came from the carbonyl compound, and this part came from the ylide. This should look quite similar to a metathesis reaction in a change your partner kind of deal where this double R group's partner was an oxygen and it flipped and took the partner of the phosphorus ylide here. So this is very similar to a metathesis reaction to form an alkene. To form an ylide, we're going to start with an organohalide like this bromobutane and treat it with triphenylphosphine. That's going to do an SN2 reaction here. To form this compound. And that phosphorus now has a positive charge. And that positive charge makes this hydrogen slightly acidic. And butyl lithium is a strong base. And so some electrons from that butyl group are going to come in and grab that proton and kick down to form I drew too many P's there. The phosphorus ylide here. If we look at the mechanism of how the alkene is formed, this ylide has some resonance, and so I'm going to draw that. You can kick those electrons down. Oh, that's going to be a minus charge and a plus charge on phosphorus. That minus charge is going to kick up and attack the carbonyl carbon. That's going to break this bond here and kick down and go towards the positive charge of that phosphorus. That's going to give you a four-membered ring intermediate where I formed a new oxygen-phosphorus bond, and I formed a new carbon-carbon bond. Again, this side of the molecule came from acetone, and this side of the molecule came from the ylide. This ylide can collapse like so to form a new triphenylphosphine oxide plus a new carbon-carbon double bond, or an alkene. Again, the two methyl groups here came from acetone, and this side of the molecule, the phenyl group and the hydrogen, are coming from the phosphorus ylide. There are a few limitations to the Wittig reaction. The first is stereochemistry. So if EZ isomers are possible, so if you have EZ isomers, both isomers are likely to form. And so in this case, we definitely have EZ isomers. On one side of the molecule, we're going to have an isopropyl and a methyl. That's going to form a new double bond that has a methyl and a hydride. So that's one potential isomer. The other isomer that's possible is this. And so in this reaction, we have the formation of both the E isomer here, where the highest priority groups, the isopropyl and the methyl, are on opposite sides, and the Z isomer, where the highest priority groups, the isopropyl group and the methyl group, are on the same side. So both of those form. So if you need one of those isomers, the Wittig reaction may or is probably not your best choice. The other problem that you can have is forming ylids from secondary alkyl halides. This SN2 reaction here on a secondary alkyl halide is very difficult because this nucleophile is quite large, and so this reaction is slow and sometimes will not take place. And so that means forming tetrasubstituted alkenes from a Wittig can be difficult. It's not impossible, but it can be difficult, and the limitation is caused by this reaction not being very fast. So the formation of the ylid is a little bit difficult from tetrasubstituted alkenes, or from secondary alkyl halides to form tetrasubstituted alkenes. The last reaction I want to talk about today is the Baeyer-Villiger reaction. And this is a reaction that can be used to generate esters and carboxylic acids. So we start with an aldehyde or a ketone and treat it with the conjugate base of a peroxy acid. This is the conjugate base of a peroxy acid. I have a OO single bond. So that's the indication that you have a peroxide, and it's right next to a C double bond O, which makes it a peroxy acid. And this reaction is going to generate an ester or a carboxylic acid, depending on whether you start with a ketone or an aldehyde, by inserting an oxygen in between this bond. The mechanism of this reaction looks like this. So we have a nucleophile in this O minus, and it's going to come in and attack the ketone and kick those electrons up to generate this tetrahedral intermediate. And then these electrons on oxygen are going to kick back down like this. This bond is going to migrate to that oxygen, which is going to kick off that bond. Which generates an ester plus this carboxylate anion. In this case, it didn't matter which side of the molecule I chose to migrate to form the carbon-oxygen bond, because both sides were the same. But if both sides are different, then you have to make a decision on what migrates. And so hydrogen is the fastest or the most likely to migrate. Slightly slower than that are tertiary alkyl groups. So that would look something like this, where this group on the other side of that squiggle So this group is migrating to form a carbon-oxygen bond. Next fastest is going to be a secondary group, which is about the same as a phenyl group. So that's these groups migrating. After that is a primary group. So it would be something like this, where that is the thing migrating. And the last one is a methyl group, is the slowest one to migrate. So if you have a methyl, that's going to be the slowest thing to migrate. If we look at a few examples of this reaction, let's start with this methyl cyclopentone or pentanone. On one side of this molecule, we have a primary group. This carbon is connected to only one other carbon, so that's a primary. On the other side, we have a secondary group. This carbon is connected to two different carbons. So the secondary group was quicker to migrate, and so we're going to break that bond and insert an oxygen in between. And that methyl group is still there. In this case, we have a secondary group and a phenyl group, which were about the same. And so in this case, I expect that you don't really favor one product over the other, and this is going to give you a mixture where on one side you broke this bond and stuck an oxygen in between. And on the other side, you broke that bond and stuck an oxygen in between. And so that you form in relatively close to equal amounts. And then in this last example, you have a secondary alkyl group and a hydrogen. And hydrogen was the fastest, and so that's the bond I expect to break. I'm going to break that one and stick an oxygen in between. And this is starting with an aldehyde, and so I expected a carboxylic acid to be the final product. That's going to wrap up our discussion of carbonyl compounds and reactivity at the carbonyl carbon and the beta carbon of an alpha beta unsaturated carbonyl.